Hey guys, welcome back. So today we're taking a look at the related rates topic. This is where we are taking derivatives, but with respect to time rather than respect to x. So whenever we have a variable that's not a time variable, you'll need a d blank dt to represent that variable. So for example, so we're going to talk a lot about areas and volumes and whatnot. If we have, let's say, an r squared in there for a radius squared, that would become 2r, then we'd have to have a dr dt next to that expression there. Always necessary to put that d blank dt next to each variable derivative. Kind of similar to when we did our implicits. We had y's, we wrote dy dx after we did derivative with respect to y there. So again, we're going to work with areas, volumes, water flow, things like that, things that will change with respect to time. So some common geometry formulas that you need to make sure you know are these area, volume, and surface area formulas. So you have your area of a circle, triangle, rectangle, and square, volumes of a rectangular solid, cube, cylinder, cone, and sphere, and then surface areas of a cube, cylinder, and sphere. Now, more likely, the more complicated the problem is going to give you, at least in terms of the AP test, the more likely they're going to give you the volume formula rather than having you have to know it yourself. Perfect example, in last year's, well, depending on when you look at this, so 2022 AP Calculus BC, one of the free response questions used a cone. They provided the volume formula of a cone for you. So you can kind of generally expect the more complicated formulas to be given, but area of a circle, pi r squared, you need to know that. I would be shocked if they gave it to you for the AP test. And obviously for those of you taking classes that are not AP, it depends on your teacher or professor. So we're just going to do some examples setting up these rates of change. We're not going to solve anything, we're just going to set it up. So an ice cube is melting. Relate the volume's rate of change with the edge's rate of change. So an ice cube. So volume of an ice cube is V equals x cubed for our side length cubed. So when we take our derivative, v is a linear term, so its derivative is just the coefficient, which would be 1, and then the derivative term dv dt. So for most of the questions, the v equals a equals whatever, it's going to be dA dt or dv dt on that left-hand side. Now the right-hand side, x cubed becomes 3x squared, and we have a dx dt. So then they would give us some information about, okay, what is the actual side length? How is the side length changing? Find the change in volume. Well, I tell you the volume is changing at this rate. Here's the side length. What is this side changing at this particular period of time? So depending on what they give you will determine which of these variables, dv, dt, x, or dxt, you're going to substitute into. But that's just the basic idea, simple, straightforward derivative. We have water level dropping in a cylindrical tank because of a small leak. Relate the rates change between the water level and the volume of the water. So we're talking about volume of a cylinder. Its volume is pi r squared h. So this derivative is a product rule, where pi is a number, so it's not part of, it's not its own separate derivative. So it's like the coefficient of having a 3 there. So those are the two pieces, the pi r squared and the h. So v becomes dv dt. Derivative of pi r squared is 2 pi r dr dt times h, and then plus pi r squared. Derivative h is 1, so just be dh dt. So you will see some basic product rule questions involving a cylinder, the cone, things that have the two different variables. Sometimes the question will work its way away from that based off giving you information that relates the r and the h together. Maybe they'll tell us what's happening at a certain period of time when the radius is half the height. So then we do half of h for r. Now we only have one variable in the problem, and we can just do a simple power rule rather than the product rule. So those are your basic area and volume questions. Obviously, we can do a lot more with that, but they're just kind of getting into what we're doing with these things. You also deal a lot with the right triangle, so you've got to remember your right triangle formulas. Your Pythagorean theorem is based off a squared plus b squared equals c squared. And trigonometry is based off your idea of SOHCAHTOA. Your sine theta is whatever the opposite. So let's say we have that a squared, b squared, c squared thing. Let's say it's this. So sine theta would be a over c. Cosine theta would be b over c. And then tangent theta would be a over b. So obviously in each one of those scenarios, if they're both unknowns or both variables are changing, you're going to deal with a quotient rule. So ideally you want to try, if you're going to use a related rate with a triangle using trigonometry, you want to try and have at least one of the sides, or one of the sides has to ideally be a constant value where it's not changing. That way you don't have to do a quotient rule, you can kind of use a basic power rule instead. All right, so Jeff is using a ladder to paint his house. Ladder's leaning against the house when Alex decides to pull the base ladder away from the house. Set up relationship of the rates of change for how high the top ladder is and the distance from the bottom of the ladder to the house. So, if we kind of draw this out, wasn't really as necessary for the other ones, but also was very helpful. So we have the height, the vertical distance, horizontal distance, and your ladder. So we'd have x squared plus y squared equals L squared. So when we take this derivative, well, we're pulling this away, so the x is changing, it's dropping down, the y is changing. So we get 2x dx dt plus 2y dy dt, and then L squared becomes 2L dl dt. But for a lot of these questions involving this scenario with a ladder leaning against a house, which is a classic related rates question, the ladder's length is not changing, so dl dt would be identified as 0, so this whole part right here would turn into a 0. And that happens with some of the right triangle questions. Sometimes it's not the hypotenuse that's changing. Maybe it's the vertical distance that's never changing. So then the dy dt part would be a 0. So it just kind of depends on the scenario they give you. But this is your basic setup. If they're all changing, everything is changing together, then you would leave them as the 2x dt, 2x dx dt, 2y dy dt, and then 2, whatever the other one is. Let's say it's L still, 2L dl dt. So we have this one with the angle of elevation, so a trig problem. Rocket is rising vertically. An observer on the ground is standing a certain distance from the rocket's launch point. As the observer watches the rocket, the angle of elevation is increasing. Relate the rates of change of the angle of elevation with the speed of the rocket. So again, we're creating this right triangle for this scenario where your observer, we'll call him O, is standing right there with the angle of elevation, and the height of the rocket is changing as it's going upwards. And then we have this horizontal distance right here. So we don't know anything about the distance the observer is from the rocket. Its actual distance, we have its horizontal distance. That's what it's talking about, the rocket's launch point. So we're going to use x and h, which is opposite and adjacent, so this would be tangents. So tangent theta would be h over x. So we do our derivative, tangent becomes secant squared, and then trig derivatives, we have to do the derivative of the angle, so that's our d theta dt. Now, as for the h over x, they're both not variables changing with respect to time. This horizontal distance is not changing between where the rocket location is and the observer. So this is really kind of like saying it's 1 over x times h. So that's 1 over x and then dh dt for that particular derivative. And so ideally you set up like this. You don't have to worry about a quotient rule. If this was something where they were both changing, then we would simply have to have it as quotient rule, which would make it low d high minus high d low over low low. So that's how the right-hand side would look if both variables were changing, which obviously you try to avoid doing that. So if you're trying to work with angle of elevation, you'll try and work with which one of the two sides, one of the three sides really, that's not changing in the slightest. All right, so that's our setup. So now let's actually start trying to solve some problems here. So they're giving us this implicit equation. They want you to find the related rates here. So they want to take the derivative with respect to t. And we want to find dy dt in this scenario. They give us x values and dx dt values. So y squared becomes 2y, and then we have a dy dt. 3x to the fourth becomes 12x cubed. We have a dx dt. And then we have 6x, that becomes 6 dx dt. So we want dy dt, so we got to fill in for y. We got to fill in for x. We got to fill in for dx dt. And you'll notice there is no y value to fill in. We don't know it. So you might be thinking, well, we're kind of stuck then. But as will happen a lot of times with these kind of questions here, we have the original scenario. So if we plug x into the original scenario, y squared is going to equal 3 times 1 to the fourth plus 6 times 1, which is going to give us a value of 9 for y squared. So y is plus or minus 3. So you'll have to be able to plug back into the original. The key really when you're doing this whole substituting values in, you're doing your derivative first. You never want to substitute a value in to begin with, because if it's changing, you're going to mess it up and not have the appropriate dy, dt, or dx or anything like that. So you always want to substitute it into the problem after a derivative occurs. So plus or minus 3 here. So you'll notice since the entire right side is going to just turn into a number, 12 times 1 cubed times 2 is 24. 6 times 2 is 12, so the right side's 36. We can think of this as plus or minus 3 inside here. So it becomes plus or minus 6 dy dt. So dy dt, when we divide over the positive and negative 6, gives us another positive and negative 6. Right, so that is our, that'll be our answer right there. They didn't give us units, so we really can't do anything else with that. All right, so we're taking derivatives with respect to t. We have another one here, so we have x squared plus y squared equals z squared, so this looks like a Pythagorean theorem setup. They want to again find dy dt, so we go ahead and get this. We have 2x dx dt plus 2y dy dt equals 2z dz dt. Now you'll notice every number has got a 2 there, so we can actually cross out all those 2's. Filling in, they give us x is 3 and dx dt is negative 1. They give us y is 4 and we want dy dt. And they don't tell us z, but they tell us dz dt is 5. So again, we're going to have to fill into the original to figure out what is the value of z. So x is 3, y is 4. If you recognize your Pythagorean triples, you'll see the value is going to be a 5 for z. But if you solve it out, we get 9 plus 16 is z squared. We get 25 equals z squared. So z is 5. Technically, this should be plus or minus because we don't really know that this is based off a geometric problem right here. So in this scenario, we should be using plus or minus 5. However, since this looks like a Pythagorean theorem question, we're going to stick with it as a Pythagorean theorem. We're going to use just the positive 5. So we can have a negative side length. In these kind of scenarios, kind of like so the previous one we did have plus or minus 3, you'll know information about the problem to know whether or not you can use a positive or negative. They're not going to have it as just one or the other. So here we know we have to have a positive because it's based off a right triangle. Anyway, so we get negative 3 plus 4 dy dt equals 25. So we get 4 dy dt is 28, which when we add the 3 over, so then dy dt is going to be a positive 7. All right, so that's how we're solving these different related rate questions. So now let's get into the actual, well, let's set up our own related rate question. So they give us here a circular pool of water is expanding at a rate of 16 pi inches squared per second. At what rate is the radius expanding when the radius is 4 inches? So we can see based off that information, they're talking about an area because the area is expanding. We have to see the inches squared. So we know a equals pi r squared is our main formula. So we take our derivatives, a becomes dA dt. Pi r squared becomes 2 pi r dr dt. So they know the area is expanding at 16 pi, so that's what we're going to fill in for dA dt. It's expanding, so it's a positive value. If they said it was shrinking at a rate of 16 pi inches squared per second, we'd have to use a negative 16 pi for dA dt. They want to know what rate is the radius expanding, so they want to know what dr dt is. They tell us r is 4. So we get 16 pi equals 8 pi dr dt. So we get a 2 for dr dt, so we need proper units though. So dr dt would be 2. It's a radius, so it's going to be inches per second. The rates are always going to be per whatever the time unit is. The question is whether or not it's going to be an inches squared, inches cubed, or whatever the unit of length happens to be. Based on, again, lengths like radiuses and heights and sides will all be the length unit, areas will be the length unit squared, and then volumes will be the length unit cubed. So that's your straightforward example. Now we have this scenario right here, which is going to use two different equations. We have a spherical balloon expanding rate of 60 pi inches cubed per second. So that's a volume. So work with V equals 4/3 pi r cubed. If this was a question on an AP test, they would probably give that to you. It is simple enough, but they would probably give that to you. They want to talk about how fast the surface area is changing now. So surface area is 4 pi r squared. So we're going to have to work with both formulas. Now, they don't tell us the value of dr dt. Because you know, if you take the derivative of the surface area, dA dt would be 8 pi r dr dt. We want to find dA dt. They give us the value of r, 4 inches. We don't know dr dt. But we do know dV dt. So we can work with the first equation, taking that derivative. V is dV dt. We get 4 pi r squared dr dt. So we can fill in the 60 pi, and it's a positive because we're expanding. 4 pi times 4 squared dr dt. We can solve for dr dt here. 4 pi times 4 squared is 64 pi. Divide that over, it doesn't go nicely, but 60 over 64 would reduce, and we would get a value of 15 over 16, and technically it'd be inches per second. Well, didn't really write the 16 too well. Let's kind of fix that. There we go. So now we can fill in to get dA dt, because we know, again, the radius in this exact moment is 4. So dr dt, based on that scenario, is 15 over 16. The 8 times 4 is 32. So we have 32 pi times 15 over 16. So 32 and 16 reduce to 2 and 1. And we get 30 pi. It's an area, so it'd be inches squared per second. And that's how the surface area is changing. It's expanding at 30 pi inches squared per second. So you'll find some of these related rates require you work with two equations at once, because both equations will have a common variable, and you'll need to take the derivative of the one to get that rate of change for the one variable we're looking for. So depending upon what they want for these kind of questions. And sometimes also they might not tell us directly the radius is 4 inches. They might tell us the volume is a certain value based off those 4 inches. And you have to kind of work backwards to figure out what is the radius based off that particular volume value. They also could have started off with the surface area is changing and use it to find out the volume is changing. And again, always watch out for the context clues of whether or not you're going to have a positive or negative rate. Expanding, shrinking, stuff like that will tell you whether you're going to have positive or negatives. All right, one more. So this is a classic kind of question you're going to see a lot with these kind of scenarios. So we've got we're creating a right triangle. I'm going to ask three different things based off the right triangle. Boat's being pulled toward a dock by a rope attached to its bow through a pulley on the dock. The pulley is higher than the boat's bow by 3 feet. At a particular moment in time, the boat is 4 feet from the dock, and the rope is being pulled in at a rate of 0.5 feet per second. So we have this scenario right here. The dock is a distance above it, always going to be a 3. We have this horizontal distance, and then we have this rope distance right here. And we want to know how fast is the boat moving towards the dock at this moment in time. The rope they give us right here, that would be how the rope is changing. That's dr dt. And it's going to be a negative 0.5 rather than a positive because you're pulling it in. One way to always tell if it's going to be a positive or negative is the value of r getting smaller or larger over time. And if we're pulling the boat into the dock, the value of r, the rope that's connecting from the dock to the boat, is getting shorter and shorter because you're getting more and more pulled into the dock, hence a negative value. So we would expect the xt will also be a negative value because it's being pulled in, that x distance is getting smaller and smaller. But the vertical distance is not changing. It's staying consistently 3 unless we're assuming the water is also rising at certain points, which they don't describe. So our formula is going to be 3 squared plus x squared equals r squared. So we take our derivative. The 3 squared is a constant, so it doesn't matter. We get 2x dx dt equals 2r dr dt. So we can cancel the 2's. We know that it's being pulled in, it's 4 feet from the dock, so that's the value of x at this moment in time. So it's 4, and we are trying to solve for dx dt. Now the rope, we don't know what that is, so we have to go back to the original equation. If x is 4, 3 squared plus 4 squared is r squared. And you should again recognize your Pythagorean triple, r is 5. And again, we have a negative 0.5 there for our dr dt. So we do our 5 times our negative 0.5, we divide over the 4, and we should get our dx dt to be a negative 0.625, and it'd be feet per second would be our units. All right, so right triangle question, classic question, either having the vertical, the horizontal, or the hypotenuse be a constant value, so its value is going to disappear and do our derivative. The 2's again cross out, we kind of fill in what we have there. Now we're going to use this information to help solve the rest of the problem now. They tell us in part B, at what rate is the area of the triangle formed by the dock, boat, and rope changing at this moment? Well, an area is half of x times 3. Again, that 3 is constant, so we don't need to worry about any sort of derivative term turning there. So we really have area is 3/2 x. So we take our derivative, a becomes dA dt, x becomes dx dt. 3/2 is still there, so our dA dt is going to be 3/2. Now that negative 0.625 is really a negative 5/8, so we can fill it in like that. We can see we're going to get a negative 15/16. And it'll be feet squared per second. We're talking about a rate of change of an area. Which again, it makes sense that the triangle is getting smaller. We're getting it's getting smaller and smaller. Overall shape being created between these two. And then finally, part C wants to know, at what rate is the angle between the dock and the rope changing at this moment? So our dock angle, there's our angle right there. So we want to use either sine or tangent, because both of them have the known value 3 being used, so I don't have to worry about a quotient rule. Now, which one we prefer? It kind of depends really on you. I'm going to use sine just because r is a nicer dr dt value. It's negative 0.5 rather than negative 0.625 or negative 5/8. So I'm going to say sine theta is 3/r, which means I'm going to say sine theta is really 3r to the negative first. Make my life a little easier. That way I'm not worrying about a quotient. I can just do a simple power rule. So our derivative sine becomes cosine theta, and then we have our d theta dt. That's what they're trying to solve for. And then we get negative 3r to the negative 2 dr dt, which would be negative 3/r squared, and the whole result's multiplied by dr dt. We're going to room on the side. Now, cosine theta, in this particular scenario, at this particular moment in time, we've got 3, 4, and 5 for the sides. Cosine is 4/5. So we have negative 3. R is 5, so it's over 5 squared, so it's a 25. And again, dr dt is really a negative 1/2. We can think of it like that. So you'll find that the negatives are going to cancel each other out here, which is nice. And then we multiply both sides by the 5/4, the reciprocal of the 4/5, to get d theta dt all by itself. So 25 and 5 will reduce to a 5 and a 1. 3, 2, and 4, when the 5 won't all reduce in the slightest, so we get a positive 3/40, and it's radians per second. All right, so that's our rate of change for the angle between the dock and the rope. All right, so there's a lot going on here. The biggest key really is just making sure any variable you're taking derivative of, you have to have a deep length dt each time, and then based off the information they'll give you, you are filling in however you want for the side length, for the area, volumes, all that kind of stuff. All right, a couple more topics. The next 2 topics will be a little bit shorter, a little bit easier. We've gone through the meat, the hard stuff from Unit 4. So I'll see you guys next time for linearization, approximating linear models, and then what's called L'Hopital's rule to use with limits.